In this video, we're going to talk about real gases, but of course, before we get into what a real gas is, we need to recap what an ideal gas is. So far, we've been treating everything in this gas unit as being ideal. And I don't want you to get the misconception that all gases are ideal when it's really the opposite. No gases are truly ideal. It's just an idea. But most gases are very close to ideal, and they don't deviate much from ideal behavior, so we can make that assumption without a lot of error being made. So the kinetic molecular theory that we learned at the beginning of the unit is really what defines for us what an ideal gas does. To be an ideal gas, you have to behave these rules, if you will. First of all, if you remember, particles are very small compared to the distances between them. So the volume of the individual particles can be assumed to be zero. So we're saying the particles are very, very, very small. And therefore, the volume of the container is the volume of the gas that it occupies. The particles are in constant, and we said random motion. And then that led to the collisions between the Waals and the particles, creating the pressure that we know gases exert. The particles exert no forces on each other, i.e. intermolecular forces. They don't attract or repel, and that's very important for ideal gases. We said that the kinetic energy of the collection of gas particles is directly proportional to the Kelvin temperature. So that was sort of a definition of what temperature meant for a gas. As I mentioned before, an ideal gas is hypothetical. No gases really do all of those things, and as I'm thinking here, I do remember that I left off the postulate for kinetic molecular theory that said all collisions are elastic, which means no energy is lost. So don't forget that one as well. But no gas exactly follows those 5 postulates. We have to correct for gas behavior when we have situations that deviate from the perfect ideal set forth in the kinetic molecular theory. Now, that could be in the conditions that we operate gases in, or it could be in the structure of the gas molecules themselves. So in this second bullet here, we say we must correct for non-ideal gas behavior when these are our conditions. If the pressure of a gas is too high, or if the temperature is too low, those are things that we can set to make gases begin to behave non-ideally. And if you're thinking why, well, the answer is almost always IMFs. If we have a gas and we lower the temperature, we are taking away the kinetic energy of the particles. So we're giving the intermolecular forces a chance to grab on and attract each other. And we know that if we get cool enough, a gas will eventually liquefy. And we don't want that to happen. So low temperatures are bad. Pressure is sort of the same idea. If we increase the pressure, what we're doing is forcing all of the particles closer together. We don't allow them to have a very long path to travel before they collide with another gas particle. And so we're increasing the chances again that we're going to have a phase change and allow the particles to kind of clump together. So those are bad things if you want to work with an ideal gas. But sometimes when you're constructing a gas, going back to sort of a maker level here, if you make a gas that is polar or has a lot of IMFs because of size or shape, then that's bad. You're not going to have a very ideal gas if it has a lot of intermolecular forces. Also, if the molecule is huge, you're violating that first postulate we just reviewed, where we said the volume is negligible for a gas molecule. If a gas molecule is huge, then when we assume that a gas is occupying the full volume of the container, that's an erroneous statement, because it would now be the volume of the container minus the summed up actual volumes of all the gas particles. So you'd always have a smaller volume than what you think you have. So again, those are conditions that make gases behave poorly, non-ideally, or we'll say real, high pressure, low temp, or if you're making a molecule, having a lot of IMFs or having a huge molecule is bad. Here we can see graphically some empirical proof that we have deviations from ideal behavior. So what we have here, PV over nRT, we know that should be a constant. And if we had an ideal gas, then that term would just go at 200 degrees Kelvin. It would just go right straight across. Okay, there would be no deviations ever. But in this example, if we graph different pressures, we can see that we do not have a constant term here for PV over nRT. The less linear these curves are, the more it deviates from ideal behavior. And you can see some of these, like CO2, has a little hook shape to it. Well, that's bad. That's in an area where you have some non-ideal behavior. It's not just pressure, it's temperature. So again, we can see that if we take a pressure here and we vary the temperature for this, this is all nitrogen gas, by the way. It should go straight across, but as the temperature changes, we can see that we have different pressure effects. We have that hook down here again at low pressures. Well, actually at low temperatures. Okay, so that's proof. This really happens. Ideal gases behave non-ideally under these conditions. So there are then gas laws that allow us to fix or correct the ideal gas law, the regular Pfeffert equation. You can kind of see here, this is called the van der Waals equation, but it's really very close to Pfeffert. Over here you have the NERT, nRT, on the right. And then over on the left-hand side, you have a couple of terms here. There's your pressure term, and there's your volume. So they're still sort of multiplied by each other, but we have some extra factors in here. We have a term here, A times N over V squared, that allows us to correct for pressure. And then over here, we have a term NB that allows us to correct for volumes. So again, that's an IMF correction and a volume correction if we have huge molecules of a gas. For real gases, the actual observed pressure is always going to be lower than what you expected. If you look at a pressure gauge for a real gas, it will always be smaller than what you would predict at that particular temperature. And again, that's because of the IMFs that we really can never control. So thinking back to the van der Waals equation, we're going to work an example problem here in a moment. But let's talk about those. Let's go take a look at it real quick. So we have some A and a B factor here. When you first saw this equation, you probably thought, what the heck are A and B? We'll talk about that. N is still moles, V is still volume, so that's typical stuff. We really need to just talk about what are A and B. Well, A and B are empirical constants. The only way you can find these A and B's are to go in the lab, run these experiments with these gases at certain temperatures, measure the pressure, known volumes, measure the pressure, and see how far off the measurements are from what ideal gas law would predict. And so you solve for these correction factors. So again, they're empirically determined. You always have to look these up in a book. And every gas that we know of has already undergone these tests. So how do you interpret these values? What do they mean anything just looking at them? Yeah, for A, remember A was in, let's scroll up again. A was in this term that corrected for pressure, so this is the IMF factor. So when you go and look at these A values, the larger the value of A, the more IMFs affect that gas. So we can see here, for example, xenon has a relatively large value of A. That's because xenon is huge. It has lots of London dispersion forces, so it's going to be relatively easy to liquefy, and so it's going to be more of a real gas compared to helium, which is tiny and very hard to make an instantaneous dipole for London dispersion forces, so it has a very low A value. And then as you get into polar gases like water and ammonia, look how large the values get there. Okay, and then so B values are for size. So the larger the molecule is, you would predict these values to go up as well. Again, helium, kind of small, xenon, a few times bigger. Okay. So that's the importance of the A and B values. So now let's do an example. In this example, we have carbon tetrachloride, and it's at 40 degrees Celsius if we have 1 mole, and then occupies 28 liters. And we want to calculate the pressure if we, A, assume that carbon tetrachloride obeys the ideal gas equation. So let's work that using PivNert and figure out what the pressure is going to be. So P will equal nRT over V. So I'm going to plug in those values. We have 1 mole. We're going to use 0.0821 liters, atmospheres, mole, Kelvin. And the temperature here is 40 Celsius, so that's 313 Kelvin. And we're going to divide by 28 liters. All right, if we do that, the pressure comes out to be 0.918 atmospheres. So that is the expected pressure for this gas at 40 degrees Celsius. Now we just talked about if it's a real gas, then the pressure would actually be less than this. This is ideal. So let's use the van der Waals equation, which I've rewritten for you up here. And let's calculate the pressure that way. The first thing I'm going to do is kind of rearrange my equation here. I'm going to go through some algebra, and I don't really want to trouble you with all the algebra, but I want to rearrange it, and solve for P. So if I rearrange that equation to solve for P, the algebra tells me that I'm going to get nRT over V minus NB minus N squared A over V squared. Now, if you want to, hit pause, do the algebra, and see if you understand where I got that rearrangement of the van der Waals equation from. Now, before I plug into this, we need A and B values, and I have those in the problem statement. Here's the A value, and here is the B value. So I'm going to go ahead and plug in all those values. We have the same 1 mole. I'm going to skip my units, if that's okay. 0.0821 for R, and still the 313 for temperature. So far it looks just like the ideal gas law calculation. Here's where it's a little different. We're going to correct for the volume, 28 liters minus, we have 1 mole of gas with a correction factor of 0.1383 for CCl4. It's a pretty big gas. And then we're going to correct for the IMFs. We have, again, 1 mole of the gas. Let's square it. Our A value is 20.4. Again, indicating we have some pretty significant IMFs. And then the V squared. So once you get it all plugged in, it's just a matter of taking your calculator out now and simplifying everything. And you can do it at your leisure. And I suggest doing it in pieces and writing it down. But when it's all said and done, this answer comes out to be 0.896 atmospheres. So we did see a decrease in the pressure as predicted from our PowerPoint discussion. So how much change is this? Is it really significant? Well, if you do an error analysis, we get 0.9, let's see here. Well, I don't want to go through all the calculations and take up a lot of time, but I did a little quick error calculation here. 0.918 minus 0.896 over 0.896. That is about a 2% error. That's not bad. If you can use the ideal gas law in some sort of process and have 2% error, that's usually means we're doing okay. Now, if you're doing a real industrial process where your pressures and temperatures, your operating conditions have a very narrow margin, you can't get away with 2% error, then that's when you would use something like the van der Waals equations. And there are numerous gas laws other than the van der Waals equations that make even more corrections for non-ideal behavior for real gases. But I showed you van der Waals because I just wanted to introduce you to the idea that we can make corrections for real gas behavior by through experimental observation. All right, so we're not going to do a lot with that, but if you do have any questions, come by and see me. We'll do some more examples together.